pretty good at it. You are beginners, so you're trying to figure out what to do. Right? And everybody's different. We all think differently, so what works for you might not work for your elbow partner. You got to come up with something. And until you do that, every question is going to be new to you, and you're going to make it angry if you can't figure it out. You have a process. The process will make things move much better. Next question. Did I get the right answer? I should ask that first.
Yeah.
Yes? Okay. So what's our next question? Slow?
53 on the same page.
53 now. You guys are asking me all the hard ones. 53. So that question so that question has static friction, right? Causing an acceleration. So you would have your car. There's my car. And it's accelerating that way. So there's my system diagram. Free body diagram is coming next. And if we read the question, we see on the free body diagram that we have our applied force from the engine. We have the normal force, force of gravity, and force of static friction. So the gist of the question is when you burn rubber, then your static friction is no longer existing because then your tires are skidding on the ground. So it's, yeah, so that's what it is. You can see that we're accelerating in the X direction based on my diagram. So I know that my net force in the X direction is MA. Actually, I did that backwards, you know. I did that for the car. If we want the tire, it should be A. That should be A. Because the tire is not spinning, right? So the tire itself is applying a force backwards on the road, and the static friction is keeping the tire going forward, so that's giving the car its acceleration. Yeah. Similar to the sprinter problem we did last week. Not that it really matters in the end, because we'll just get a negative number. All right, so what's my net force equation here, based on my compass system? Ashley? Can't fit it out there. You got static friction minus. Yep, good. So your static friction is causing the acceleration. The applied force is trying to go backwards, and then we have A. And then as we go through our routine, we put in our equations that we know. Alright, we put in our routine, our equations. We don't know Fn, so we go to the y direction and we should get the answer. Jaden?
Can you explain why gravity is more popular?
Sure, I just made a mistake there.
Oh.
Okay, I was really confused.
Maybe it's a race in Australia and I thought I'd make it from our perspective.
I know all this.
There we go.
Sorry, Cal.
Yeah.
I didn't even do all this. I just did fx equals ma and then fs equals ma, and I figured out an answer. And like I just did fs is going left, and there's no force applied.
Okay. Isn't there an applied force in the question? No?
It's just acceleration.
Oh, just acceleration? I'm confused why there's not one then.
Yeah, I was pretty confused too while doing it, so I just
Yeah.
this way and got the right answer.
Yeah. I don't have an answer for you there.
Maybe you just take part of the whole, don't think of the wheels.
Yeah, maybe you don't think of the wheels, which would be kind of weird.
Well, no, I did. I just derived like equation for friction, and then I found explaining forces instead of the and then I started.
I'm thinking about that.
Yeah.
I get what you're saying
Let's
too.
do fs equals ma and then
Yeah.
all of that.
I think it's all like that. Yeah, because you don't have that thing. So you have it like that to get your answer then, right?
What?
You have it like that, right?
Yeah, and then you just find the y-axis. Oh no, fs is going left. When you go now, it doesn't really matter, I guess.
Well, the flag question?
Is it a flag?
Oh no, it's a sign. It's a sign.
Yeah.
I thought it was a fun question.
It's kind of weird.
It does look kind of weird. Yeah, I thought it was a fun question. I'll give it to you guys. So on the flag question, or sign, I guess. So the wind is going to the right in my question at a constant velocity, right? And it's stationary as far as I know. So my velocity is 0. So I'm still going to make up and down, positive directions, traditional right and up. What does the free body diagram look like for the sign? In this case here.
So there's gravity going down.
Yeah. Yep.
Then there's tension going in top left.
Yep. Yep.
I don't know if that's like a force applied, but for wind going right.
Yeah, we can, yeah, I'll just call it applied force. I like that.
That's all I got.
That's all there is.
There's no FM.
No, it's not on the ground.
So there's like roof.
Who cares about the roof? We're focused on the sign.
All right.
Sign's on the ground. Eric?
No, we can also just put the angle in.
You can put the angle in the other spot too if you want. You could do like a purple triangle if you'd like. Yeah, you can put the angle there if you want instead. Whatever makes sense to you. Do the same. Jake?
So if there were only one road, wouldn't the sign kind of be flapping around everywhere?
It would be like moving in and out of the board. Like, who knows what the flag's doing? You're right. Nor is wind ever constant. So in this particular instance, this is what we're given. Let's not think too hard about what we really would be doing. You're 100% right. Normally, yeah, if it wasn't the wind, there'd be a second thing down here, like a flag on the flag post. Yeah. Ashley? What about?
I thought it was like, it was always closest to like the middle.
I'm just going off the picture, and the picture that gave me this angle up here,
Mm-hmm.
so that's why I drew it up there.
Okay.
If it makes you feel better or you understand it better here, then draw it down there. It wasn't in the description, it was just like, there's a picture and I just copied the picture.
Okay.
Okay? So what's the question? Find FT, I'm guessing?
Yeah, find T and then find the angle.
Yeah, so again, same steps, right? So we have this, we know that's 0. We start in the x direction, which is 0. We're gonna get FTX minus we have FA minus FTX equals 0, right? Because I said right's positive, which is the direction A is going in. So then we're going to get FA is equal to FTX. And then in the Y direction, also 0. Up is positive, so we have FTY minus FG is equal to 0. F2y is equal to mg.
Why is it 0? How come it's not accelerating?
Because the question tells me it's not accelerating.
Does it?
It says it's at rest, probably. A strong horizontal wind exerts a sign. Yeah. It's not moving. It's just supported there. So you're right, it's not like explicitly said it's at rest, but it's not going anywhere either.
I guess that's where I made a mistake.
Yeah. Yeah, if you put MA in there, you're going to get stuck. And then you have your values for FTX and FTY. So this is very similar to questions we've done in the past, where I'm just going to redraw this down here, right? So here's my FT. So again, we have FTX, FTY, you go up and across, and you can put your angle wherever you want it to be. So I'll just keep it with my picture up there, right? So use the Pythagorean theorem to find FT, and then tangent to find the angle on it. All right, so it doesn't follow the same trend as we did in every other question today. We weren't asked to find a hypotenuse today. Yes, so that's just a different type of question.
Wait, so you find the components? You find the...
Yep, you found the components in the two last black lines up there and use them to find the hypotenuse in the purple triangle. Right? Same as displacement questions, same as relative velocity questions that we've already done. .43 on 102. Um, 43 is the same as the flight question. the one we just did. Only you're given the angle this time, and so when you look at it, we have the roof, we have the trapeze, we have our person hanging on the trapeze, and there's a rope holding the back, right? So, and this is 35 degrees up here. So in our free body diagram, we have our first tension going up that way. It's 35 degrees in there, about 35. Stage, yeah. All right, so we have that for the tension, first tension. All right, we have ft2 going that way and ft going that way, right? So if we do our same equations that we did before, right, we have our, they're just hanging there, so in the x direction it balances out. We have ft1x minus ft2 is equal to 0. And then in the y direction, you have ft2 or ft1y. Right? And then we're trying to find both tensions, I think, in the question, right? So over here, we work over here, we have ft1 sine 35 equal to mg. Right? And then you can use that to find ft1. And then you can flip over to the x direction to find ft2. Because you know everything in the y direction except for the ft.
So why is the tension going horizontal, not like at an angle?
Look at that's what the picture's telling me.
Wouldn't they like bend up?
No,
Alright.
it can go up, right? It can go any direction you want it to. If the person's hanging there, it would go up. But I'm sure that this part here, right, is attached to somebody over here. Maybe they're pulling them back, and then gonna let them go so they swing back and forth, right? All right, like if you know, on a kid with a swing, right? You pull them back, you're pulling them backwards, right? So the chain on your swing is taking up the load of gravity, and it's only your applied force pulling backwards.
Yeah, I just didn't really see why it was doing that, so I see.
Boom.
Can you just do this diagram? Just have 55 on 144.
Yeah, sure. Sorry, which one?
55 on 144.
Ooh, that's a fun one. this is a uniform circular motion question. So for this question, so we do a bird's eye view of this question. So looking down on the cage that they're in, right? So if you're looking down on the cage that they're in, right? The person's on the wall just going on a circle, right? So it'd be like driving on the wall in the classroom here, right? This is my top view. My profile view would look like this, and I would just see the back of them as they go around the cage. Right, so this would be like pointing in the board, coming out of the board like this. Does that make sense? Okay. So if we use the profile view to generate our free body diagram, right? We have our normal force sticking out of the cage, right? They're on the wall, so it goes sideways. We have the force of gravity going down. The gravity always goes down. And the question to ask you, what does the force of friction need to be for the tires so they don't slide down the wall? Does that help you out? Yeah. And then you just go and figure it out from there. Jake?
Can you explain why number 12 on page 99 is text?
Probably. I hope so. In a tug of war between two athletes, each pulls on a tension on the rope. The tension on the rope is 600 newtons. And the answer is false. Is that what you said?
Textbook says, yeah.
Textbook says it's false. So if you're looking at the rope itself, it would have a net force of 0 on it because it's 300 left, 300 right. Right? So it would be, that's what would make it 600 newtons false. Yeah. Yeah.
You do number 64 on what is it, number 4.
$64, the box going down the incline plane. Oh no, it's not. It's just on flat surface.
Yeah, on the rock surface.
So for this question here, you have a box. It is accelerating, right? That's what it says. It would be decelerating. Yep. That's correct. So my velocity would be going this way, but my acceleration is going to be going that way. So if I make that my positive x direction, So then, Andre, right, just have your kinetic friction slowing down. Right, there's no applied force.
I did everything right. I think there's I forgot the exact question. I forgot to see the acceleration.
Okay. So you're good?
Yeah.
Okay. So Olivia typed in a question here. She said, why would two objects having different speeds hit each other with the same force? Any ideas why that would be? So if you had a slow moving car and a fast moving truck, they hit each other. Why are the forces of impact the same on each car? Jake?
Newton's third law.
Newton's third law. How does that apply to Newton's third law?
Because they're pushing against each other, so the forces are going opposite.
Yeah, good. So when you have the collision, right? Anytime you have a collision, you have equal forces on each object in the collision. How they accelerate during the collision is going to be different based on their masses, but the force that impacts is going to be the same, whatever that might be. Yeah.
There's a force mass times acceleration. Cars would have a different mass. So what if they do different?
So no, because your forces are constant, your masses are different, so your accelerations will be different. Yes. It's not, the way you were thinking there is that because their masses are different, the forces have to be different, but I would consider the accelerations are the same for each car in the collision, which they're not. Yeah. Eric?
For that question on the board, would kinetic friction be acting in the direction of the acceleration?
In my diagram it does, yeah.
And which question was on the board again? I didn't hear.
I don't know what board, it's like 60 something. 64 on page 104.
Okay, thank you.
Any other questions? Which one? 22. Express the net force acting on the following object. So what's the net force acting on an object moving at a constant speed? Anybody tell me? Eric? 0. So the first question is going to be 0 because the raindrop falling at a constant speed. A cork floating on still water. What do you think it's going to be? Eric?
0 again.
0 again, right? Because it's not moving. It's 0. Yeah, the magnitude is 0. Stone with a mass just after it's dropped from a window. This one you'd have to calculate, right? Because that would just be gravity, right? So whatever, it'd be 0.98. We do the math. And it says the same stone at rest on the floor of the train, which is accelerating at 1 meter per second. And that should be 9.8 newtons, right? Because it's Newton's second law. Net force equals mass times acceleration.
Which was also static.
Oh no, like that's a good question. So in that, it's telling you what the acceleration is, and the questions ask you just to find the net force. So you're right, static friction is causing the net force, but it's not asking what anything beyond just what is the net force. Yeah. Jada?
38, I was confused on like Like, I wanna know if you want us to stay for
Same question?
that.
Or is it like same, like 102? Describe how you use this textbook and a piece of paper and a desk to demonstrate Newton's first law of motion. That one? Well, that's just, that's what we saw the Pope do, right? Well, it's, like, you can come up with lots of different answers. Like right now, my book is Newton's first law of motion because it's not moving. Everything's balanced, right? You can put a piece of paper underneath it, right? Like this. And then pull it out really quick, and the book doesn't move because its inertia keeps it still, even though this moved out from underneath it. Yeah, there's lots of different answers there.
Well, 140-17.
What about
Can you answer that one?
it? Sure.
We just wanted to know like what you're looking for in an application question on how you want it to explain. We knew the answer, but we didn't know how they could get people to
All application questions are the same. I want you to connect it to some physics concept that we did in our unit. Right? So if you look at 17, two cars with the same mass are driving around a curved road at different velocities. Which one will have the greater centripetal force? The one going faster, one going slow. Right? So obviously the faster one's going to have the more centripetal force. Right? You can relate it to the equation and show that your AC is equal to V squared. So if it's, no, sorry, this is mass. No, same mass, different velocity. So the one that's going faster will have 4 times the amount of force acting on it because the speed is squared in the equation. Yeah. So you would, yeah. So like a level or one of the two answers that the one that's going faster has more force. That's good, but better answer is that it has 4 times as much acceleration because of the relationship in the equation. Yeah. It's a good question. Phone.
I'm still doing again Texas 55, but would you ask something like C on 55 on 144?
I have before. What is that one?
It's still in the middle of the page, but
Did you do A?
yeah, I did A and B.
Right. Yeah, C is a totally different question, right? So I would either ask you A or C. I wouldn't ask you both in the same question.
But like, how do you start C?
How do you start it? So that's a vertical circle, right? So they're switching you moving, right? So when you're at the top, right, your normal force and gravity are going in the same direction. If you're at the bottom of the circle, your normal force and your normal force and gravity are going in opposite directions. Each are equal to MAC, and then you find the at the ends of both top and bottom, and that would be the force that you need. Where should you guys be?
America.
America? Awesome. Any other questions? I love this. This is a great day. You guys are asking lots of questions.
So for the test, are you gonna like give us questions that require us to infer this like accelerating amount, or you just tell us it's at rest or accelerating?
Depends on- I can ask you whatever I want to ask you.
Okay.
Yeah, because I could ask you, I don't really get your question, because I could ask you, I give you the static force, the static friction, and say like, here's the applied force, here's your force of static friction, is it
No,
strong enough to go?
That's not what I mean. I mean if like you have to know if it's accelerating or mass, we're accelerating or at rest, but like you can go like 50-50 and you just like choose one.
Have you had any questions like that in your homework?
Yeah.
Like what? What was the question?
I can't remember which one, but like you did on the board. It was like you had to like find something, and then it was like I put acceleration, so it was at rest.
It was in the question though, it was at rest.
Like your question didn't say it was at rest or accelerating.
It did.
Did it?
Yeah.
Okay.
Like I'm trying to think of a question where it wouldn't, you're given a hint as to what it's doing. Either it's moving, either it's accelerating, it's in kinetic equilibrium, or static equilibrium, right? Those are your three options in a question. Right? Two of those are Newton's first law, and the third one is Newton's second law.
Yeah.
Right? So, like based on the story, right? I think it was a flag question where it was on an angle, and just the way they worded it, it wasn't going anywhere.
Okay. So just just be careful with the wording. I guess.
Because you have to picture what's happening,
Yeah.
right? Usually it tells you what it's doing.
Alright, I'll just be careful with the wording now.
Yeah, because you have, what do you have? Static equilibrium, kinetic equilibrium, accelerating in a straight line, and going in a circle.
What do you think
Right.
kinetic equilibrium?
Pardon?
What kinetic equilibrium was that?
What do you think it is?
It's like, equilibrium means it's at rest. So.
No, it doesn't mean it's at rest. Sorry, what'd you say? What type of equilibrium?
No, you said it wasn't equilibrium.
I missed what type of equilibrium you said.
Equilibrium. Right.
Yeah, equilibrium does not mean it's at rest. No.
No?
No. That's why there's two types of equilibrium.
Okay, what's kinetic?
Pardon?
What's kinetic then?
What's static?
Static means like, not kinetic, so it's not moving.
Pardon?
It's not sliding.
So what's it doing then if it's not sliding? Ashley? Yeah, it's keeping an object at rest, a static equilibrium. What does the word kinetic mean? No, kinetic doesn't mean sliding force, no. What does kinetic mean? Yes. Yeah, kinetic, Eric pointed out, kinetic means moving. So kinetic equilibrium means it's moving equilibrium, so everything's still balanced, but it's moving. All right, this is kinetic equilibrium. I'm going at a constant pace in this direction. Right? Newton's first law.
So acceleration is still zero, so it's like a constant speed.
Yeah. Uniform motion is Newton's first law. Right?
Okay.
Uniform acceleration is his second law.
Right.
Then the forces are balanced out. As soon as it's equilibrium, that's Newton's first law. then whether it's stationary or moving might tell you the question, but at the end game, you don't really need to know that. You just need to know it. As soon as you see equilibrium, everything's balanced. That's what that term means. Eric?
When you're driving a car around a corner, for example,
Yep.
where is static friction acting in the ratio?
It's static friction whenever something's in motion is providing your movement forward. Right? So in a car, the car's inertia wants to push it towards the outside of the circle. Right? So your static friction goes towards the inside of the circle to counteract the inertia.
So the inertia wants you to go inward?
That's why it goes in. No, you're
Go outward.
outward, right? Have you ever played on a, like, as a kid, did you ever play on a merry-go-round? You know, like big disc that you can stand on and you'll get your friends to push you really fast, and if it's too fast, you fly off. Right? So that's what it's happening here, right? Your inertia flings you off that ride. So if you're not holding on to anything, the only thing keeping you there is your static friction in your shoes, which is towards the center of the circle. Does that make sense? Yeah. You guys want to take a walking break? Been lots of questions. I don't know if you guys have more. We have an hour left of class. As always, we can take a break. This is a quick review here as some different terms that I know you've heard before, but whether you are remember what they are. That's a different story. From any science class, do you remember the difference between the terms of open and closed systems and an isolated system? I know you talked about this in chemistry, sometimes ecology, and physics last year. Andre?
I know like open and closed circuits, is that related?
Sure, maybe we can start there if you want.
So like an open circuit is when it's like not running, since like it's not